Hi everyone, Dr. P here, and in this lecture video we're going to take a look at covalent bonds, in particular the strength of covalent bonds. Now you may remember from the video 1, and I'll go ahead and I'll put that back up here. And in our covalent bonds we have shared electrons that act, these pairs of shared electrons act as a kind of glue to hold the bonds together. And so when we have separated atoms, they're at essentially zero energy. If our atoms are literally right on top of each other, we would eventually get infinite energy, or really, really high energy, because we can't smush two things into the same space at the same time. But at some optimum distance, the combination of our two nuclei, or two atoms, and then one pair of electrons gives some lowest energy, an energy minimum. And that energy here, in this case for hydrogen, H2, is our bond energy, and for hydrogen it's minus 458 kilojoules per mole. So remember the delta H in the lattice energy that we looked at for ionic bonds the last time. This is looking at something similar but slightly different, because our electrons are really kind of localized in between our atoms, and that's a particular kind of model of bonding, which we'll talk more about when we talk about how we represent chemical bonds. Okay, so let's go ahead then and take a look at looking at some of these energies. So actually, let's call it covalent bond energies. All right, so if approximately 1652 kilojoules are required, that is, we have to input that much energy to break 1 mole of CH4 into carbon plus 4 moles of hydrogen, then we would divide this by 4, because we have 4 carbon-hydrogen bonds, and we'd have 413 kilojoules per mole per CH bond. And that's our bond energy. And we can use this then for other compounds. So if 1578 kilojoules per mole are required to break 1 mole of CH3Cl into carbon, 3 hydrogens, and chlorine, and we know that we have 413, if CH energy is 413 kilojoules per mole, then we can calculate that the CCl bond energy is going to be 339 kilojoules per mole. So I just multiplied 413 by 3 and subtracted it from 1578 here. Okay. So it turns out that these bond energies are actually, it's not quite this easy. And bond energies actually are sensitive to the environment. So what I just did here is not exactly what scientists do, though it is similar. It's using Hess's law. Um, what we have is, for example, CH4 or CH bond energy is 413 kilojoules per mole. But in CH3Cl, our CH bond energy is not actually 413, it's 380 kilojoules per mole, because it turns out our CCl bond is not actually 339. In CHF3, our CH bond energy is 430 kilojoules per mole. So the presence of those three fluorines gives us a stronger CH bond. And then if we have C2H6, our CH bond energy is 410 kilojoules per mole. Notice that that's pretty close to the 413 there. Also, the number of pairs of electrons shared affects things. So we could have a single bond, which is one pair of shared electrons. We could have a double bond, or we could have a triple bond. Now, I'll have you guys start thinking about this now, but we may talk about this in lecture. Think about why there may or may not be such a thing as a quadruple bond. Can you actually have a quadruple bond? And over the next 2 chapters, we'll try to figure out whether or not you can have a quadruple bond. Okay, so we can go ahead and do a little more quantitative stuff here if we want. And really in this chapter, I don't want to get bogged down on too much quantitative stuff, but let's take a look at bond energy and enthalpy. And so our symbol for bond energy is going to be a D, a capital D. That's going to be our bond energy. And of course, enthalpy is, in this case, delta H. So I could write out, for a reaction, delta H, so for a reaction, I'll abbreviate that RXN, delta H equals the sum of the energies of the bonds broken minus the sum of the energies of the bonds formed. So what's going on here is that this here is our energy required to break things apart, and then this is the energy that is released. So for example, we could look at the combustion of methane. We have CH4 gas plus 2O2 gas goes to CO2 gas plus 2H2O gas. So our delta H is going to equal, well, we have 4 CH bonds that are broken. So 4 times DCH plus 2 oxygen-oxygen bonds. So that's 2 times D, O double bond O. Okay, so we've got that guy. And then minus, we're making 2 sets of CO double bonds here because carbon dioxide is, I happen to know it has that structure. And these indicate double bonds. So I've got 2 double bonds. So I've got 2 DC double bond O plus 4, because I've got 2 OH bonds in each water, and I've got 2 of them, so 4 DOH. And I can go ahead and plug these in here, and I could get 4 times 413 plus 2 times, I can look this up, 495 minus 2 times 799 and plus 4 times 467. And if I go ahead and add all these up, I end up getting minus 824 kilojoules. Now we can compare this to delta H naught from delta HF naught values, and that result is minus 802.5 kilojoules. So it's not too bad. 10% of 800 would be 80, so we're off by about 20, so it's about a quarter of 10%. We're off by about 2.5%, so that's not too bad. Okay, so this way of kind of evaluating or estimating the delta H for a reaction based on which bonds are broken and which bond forms can be quite effective. All right, well, like I said before, I don't want to get too bogged down in the numbers in this chapter because we've got some more fun stuff, and that is we're going to draw some pictures. And in the next lecture video, we'll go ahead and take a look at drawing representations of chemical compounds, covalent compounds, using what are called Lewis structures. But until then, stay safe out there. Bye now.